So the object class, everything derives ultimately from the object class. It is the ultimate superclass of everything else. And it gives us the things like equals and toString and whatever other methods that we can override. So for example, the equals method. For a class that doesn't have its own equals method, if you try to call dot equals, it just uses the one that equals that the object class gives you. And all that one does is to compare memory addresses. That's the only way that it checks to see if they're the same, right? So say we were going to make a class. What lecture are we on, gang?
I think lecture U.
Sounds good.
Yeah, that's it.
I do want to main class this time. So say we were going to create some kind of abstract class up here at the top. Whoopsie, whoopsie, whoopsie. And all I had was one variable type, which was name. And then we had something that inherited from that, like a lizard. Can I type, please? There we go. All righty. And so its constructor is going to set the name of the animal. So public lizard name equals lizard. So down in main, if we were going to create two lizards, then, and we wanted to see if they were the same lizard or different lizards, or if we had two different kinds of animals that extended that class, like fish. So class fish extends animal, and its constructor sets the name of it to fish. So down here, why do you give me errors? Because I don't have enough closing braces. Fish, F equals new fish. Lizard L equals new lizard. And we wanted to compare them to see if they were the same or not. Of course, they are not the same. We would have to define what kind of criterion makes fish the same or not. But what if we had a second fish? And right now, fish don't have any data, right, to compare that are of interest at all. But if we wanted to be able to compare them, if we did this, if we said fish F is equal to F, and then we check to see if they equals, it will say that yes, they do equal. And it makes sense that they equal because they're both pointing to the same object. It's not copies of the same object, but they both point to the same object. Semicolon. All right, so they are the same thing because they have the same reference, right? I guess we ought to make this a little bit more interesting and have some kind of value in here that indicates something special about the fish, like whether it's freshwater, saltwater. So after the fish is created, we can pass in a type. and it's going to be fresh or salt, right? So string type. And so water is equal to the water type. So when we create a fish, we better specify whether it's a freshwater fish or a saltwater fish. That one's a saltwater fish. And we're going to make another fish that's a saltwater fish. So F2 is equal to new fish. Well, let's make one, yeah, that's salt. And we would like for it to say that they are equal fish because they're both the same kind. You don't need to tell me that. It doesn't help me. I wish you would just run it. All right. And so when I run it, it's not going to tell me that they are the same. So we would need to write a dot equals method. Now, when I started this little lecture off, what I was wondering is how you could make it so you can compare different animals of different types and have them come out to be the same. And I'm not really coming up with any way that that would work. You could add a dot equals method to the animal class. But then what would it be comparing? Because the specific information is buried down inside, right, the individual subclasses. But anyways, let's check to see if these things are the same. So public Boolean equals, this fish. Well, we're going to do it the correct way. Object O, right, like that. How about just object O? We're going to compare ourselves to the other one. First thing we're going to do is we're going to see if we are equal to ourselves. So if O is equal to this, it's the same thing. So return true. And then we're going to use is instance of to see if what the other thing is a fish, because if what was passed in wasn't even a fish, then it's absolutely not equal, right? What if we were trying to compare a lizard to a fish? We definitely don't want it to allow that. So if O is instance of fish, or if O is not instance of fish, so if O instance of fish equals false, then return false, because we know they're not the same. And then we would just check our individual member there, right? The water type. So if now we need to cast it to be a fish in order for us to access the specific types of this object. Because right now all it knows about it is that it is an object. It doesn't know that it is a fish, but we have proved that it is a fish, so we have proved that it's safe to do this. Fish other is equal to fish, that reference, right? And so now we can do if this dot water dot equals other dot water equals false, right? If the comparison is false, of course, I could always just use the exclamation mark here to do the same thing. And then I'm going to return false. Otherwise, if we get there and it's passed all these checks, then we're going to return true. So now that these fish are the same, we should get our equal fish method back, message back. Or not. Is it going into our constructor? I mean, our comparator. I'm going to put a breakpoint there. I'm going to debug. I'm mystified. Okay, so step over. We have created one fish. We have created another fish. Now we're going to check to see if they equal. Oh, no wonder. I forgot to actually call dot equals on it. That was a dumb mistake. Of course, you cannot compare two objects doing that. So I call if f dot equals f2. Then print equal fish, else print not equal. I was mystified because even though I had set a breakpoint here, it didn't trigger it. And of course it didn't trigger it. I never called dot equals, and just got through teaching a C++ class where you can overload the equal operator so that you could actually do things like that, and it would call that method. But C++ does not allow operator overloading. All fish are not created equal. Okay, so when we run it, we'd better see it say equal fish so that we can move to the next slide. All right, so they are equal fish. And if we had extra members, if we had extra data variables besides water, then we would definitely want to add a dot equals for each one of them. So here's my question, and I don't know the answer, but what if I had another kind of fish that had its own attribute? How would I check to see if it was equal, right? What if I created a fish called a shark and had its own attribute, right? And so then the shark class could have a constructor that would create a fish, and let's just pretend that all fish are saltwater fish. So the constructor would need to call the superconstructor and say that this is saltwater fish. And what if it took a number of teeth, right? And so the constructor set this dot teeth equal to teeth. And it extends the fish class, right? Okay, so if I want to write an equals method for shark, do I have to do all of this check here? Do I have to check the fish type itself? Do I have to write an equals method? Can this equals method, if I was going to add one, take advantage of any of this, or do I just have to write another one that completely replaces this one, that overrides it? And I think that that's the case. I think that if I'm going to do it, I'm going to have to write a equals method that does all of this and checks the number of teeth to see if they're the same. I'm gonna have to ponder that. Maybe you see what I mean. It's like I've already written something that checks a lot of things. This thing may have had 20 attributes, right? Not just one or two. It may have had 20 attributes. And say we'd written a nice equals method that checked all 20 of those attributes. And then when we wanted to subclass it, when we wanted to inherit from it, and we needed to add a dot equals method to this, is there any way to leverage all of that? I don't know. So we know what an equals method does. It just checks the members of the items, of the elements reference that's passed in, and compares it to the values that are set for this reference, and checks to see if they're the same. You ever going to show it? Oh, come on. Cute. They pose the problem and they don't show the answer. Maybe down here in the little notes. Nope. Yeah, here it is. Way down here in the notes. Oh, they added a check that I didn't. Is the other object a null? If you're comparing it to null, return false. That sounds like a good thing to do. I probably should have put that in there. Otherwise, return whether the car make matches and the car's year matches and the car's color matches. Well, I like mine a little bit better because it allows them to pass in an object of type something other than a car or something other than a fish. And why would you want to support that? It could be that you would want to increase the flexibility of your class so that, like, if you had a floating point and you had an integer data type, you don't want to only allow comparing of integers and integers or floats to floats. You'd want to be able to compare one to the other because sometimes they do equal, right? 3 is equal to 3.0. So you do want the option of being able to pass in an object of a different type when you call it. So down here, I'd like to be able to do things like this. If, f dot equals L for the lizard and not have it be a syntax error. Now, it's definitely going to return that it's not, right? But there may be some circumstance where we want to create something else that would, if we compared it to our fish, that it would say that it was true. But that check for null is not a bad idea. I have no idea why you would ever want to say if f1 equals null, right? That makes it sound like we're checking to see if it is null. And it can't be null because we're calling a method on it. And so if f was a null reference, then it would crash when we tried to invoke a method on it. But anyways, I guess it could be safer to add that on here, right? If O equals null, return false. I don't know why I'd never noticed that they did that. I guess because it's in, microscopic print at the end of one of their slides. So anyways, you do your rule out things. Are we null? Are we checking against ourselves? Why are we checking to see if we're against ourselves? Because we don't want to bother doing the rest of the work if O is a reference to ourselves, right? If we do this, if F equals F, well, of course that's true. So we don't need to go any further, right? So we rule out whether it's null. We rule out whether we are ourselves. We rule out if we are not of the right type. And then we use we use casting in order to create a reference to that object so that we can compare to see if this is equal to the other, right? And right now we only have one attribute of import. I guess we could check the name as well, right? I mean, since we have it here. If not, this dot water, this dot name dot equals other dot name, return false. And we would just go on down the line checking all the attributes. ToString method. We've talked about ToString so often, I don't really see that we need to talk about it again, right? It just represents the data in a string format so that you can quickly print it out on the screen. Are we good on that, guys? I mean, I can talk about it more, but we've been doing that since like week 2. So please say something if you want me to not be skipping these slides that I'm skipping.
It's fine. I remember ToString.
All righty. So all primitive wrapper classes have ToString methods that give a string representation of the given primitive value. So if you create an integer and you set it equal to 22, then when you call its ToString method, it does return 22. And the double ToString method would return 123.45. So polymorphisms, different types of objects respond differently to the same method call. To implement polymorphic behavior, you declare a general type of reference variable that's able to refer to objects of different types. So right now we have let's skip our fish, lizards, and whatever, and go with another. We're going to create a class called shape. It's going to be an abstract class, and every shape needs to have a getArea method. That's all we know about it. So abstract public double getArea. We're not providing a body for it, but we are guaranteed that every shape will have to implement a getArea method. And then we could have a shape type, right? A string type, public string type, whatever. So the circle class the constructor for it needs to set its radius. So we're going to have a radius. And public circle double radius. This dot radius becomes radius, and this dot type equals circle, just so that we have something that, like if we want to call toString or something on it, then we can print out that it's a circle. But we could actually do that up here. We could add a toString method that said that this is a circle. Why don't we do that? So I'm going to come up here, whoopsie, whoopsie, whoopsie. And so he's going to get a public string toString, which just returns shape space plus the type. So to say shape circle or whatever, or shape equals, right? And he's complaining that I have not implemented a getArea method. And that's absolutely true. I have not. So public double getArea 2 point pi r squared return math.pi times radius times radius. And this is an override, so I'm going to click that. Now I'm going to make something else that also has a getArea method. Class square extends shape. Same business, except it doesn't have a radius. It has a side, right? So double side, public square, takes a variable called side and sets this dot side equal to that. This dot type is equal to square. And then he needs his own getArea method. Forgive me for being lazy, but I'm going to copy this getArea method and just paste it and change its formula. And so the value of the area of a square is just side times side, right? That's not enough. I mean, that's enough. I don't think I need to go and make any more. So what if we go and create an array list of shapes equals new array list. Definitely have to add an import for that. And now let's add a couple things to it. slist.add a new circle of radius 10. slist.add a new square with a side length of 10. slist.add new circle of radius 20. And slist.add new square with side length of 20. And let's step through our array list now and print out some information about it. For shape V in the shape list, let's print out the shape. System.out.println plus quote has an area of end quote plus v dot get area. Open parentheses, close parentheses, semicolon. All right, and so the circle has an area of that. The square has an area of that. 10 times 10 is 100. The next one with a radius of 20 has an area of that. That circle has that, and that square has a radius of that. So we have different objects responding to the same call as though they were objects of the same type. And in a way, they are objects of the same type, right? I mean, they're both sharers, but they are very different in their underpinnings. You know, we could have a shape that, you know, was drastically different, and it had it had not only a height and a width and a depth and a this and a that and the other, but as long as it had a get area method, and it has to, because that abstract declaration insisted that the class have it, or else it would not compile, that we could treat them as though they are all the same thing. So notice that I was able to call it by its generic type, right? I was able to say that each one of these is a shape. I did not create a list that was made first of circles and then another list that was made of squares. I was able to make one of shapes and then pile both list and squares into the array. So that's polymorphism. Polymorphism is when you have different objects that respond differently to the same method call as though they were objects of the same class, as though they were objects of the same type. And so, blipping back to the homework, I did pull a fast one on you and said that I was going to give you one assignment, and then I gave you another one. Let's go and look at what's different about it. So you're going to have a coin class. And then from the coin class, you're going to make a penny, a dime, a nickel, and a quarter. I hope you know how to do that from the examples that we've given so far. You just make an abstract class called coin. Oh, what do you know? If I give you the sample here, that makes it not too hard. Well, forget it. I'm not going to even talk about it any further. No, I'm kidding. So the abstract class, we have a value here, and then we have a constructor that sets the value. And it might be nice if also it had a name, right? So that you could say that this was a dime and it had that amount. If you feel like doing that, if you felt like adding another method here, right? Final string name. And then the constructor for it could accept a name as well as a value. So when we were calling our super constructor, we could say, I am a dime and I'm worth that. Right? I think that'd be pretty neat, because then you could create a two-string method right here. Add a two-string method to your coin class, and it would print out both, you know, its name and its value, if you feel like, right? Anyways, and then your class, excuse me, your piggy bank is just going to add an add member that accepts a number of coins to add and then the specific type of coin, right? And so you create a dime and you can pass in 10 dimes if you want, or you create a quarter and you pass in 10 quarters if you want. And so that's what's talked about over here, right? I want to add some coins to it, and so I'm going to create a new penny. I want to add 20 pennies to it. So int number of coins is equal to 20, and int added is equal to add coins. We pass in 20, and we're passing in our penny class so that it knows the value of them. It knows the value of a penny, and it would try to add 20 pennies. However, it can't, because it's already got 45 in them. So there's only room for 5, and so the class is supposed to go ahead and add the value of 5 coins in it, but then it can't put the rest of them in the bank. The bank is full. So this function is supposed to return the number of coins added. And if the number of coins added does not pass the number of coins that was passed in, then the bank was full, and we ought to tell the user that, right? Here's an example. The bank already has 50 coins. So no matter what, no matter how many we add, it should return 0. So how are you going to write your add coins method in order to handle that? I think I would just write a for loop, right? For x equals, up to the count of the coins that are supposed to be added. And I would keep adding a coin over and over and over until I ran out of room, right? Until my count exceeded 50. And then I would break out of the for loop. So to implement polymorphic behavior, you declare a general type of reference variable that is able to refer to objects of different types. So they have both dogs and cats, and they're both pets. And a dog's toString method returns woof woof. A cat's toString method returns meow meow. So then no matter what kind of object we ask for, no matter what kind of object we create, here's our little code. Do you want a cat or a dog? Which do you prefer, cats or dogs? And if they type in D, it makes a new dog. If they type in C, it makes a new cat. And then it calls the polymorphic method call toString. It happens to know that both of those objects, both of those classes have toString methods so that they can be called interchangeably on it. All right. So dynamic binding. Polymorphism is a concept. Dynamic binding is a description of how that concept is implemented. So how does it figure out that when I call get area down here, when I'm stepping through my list of shapes and calling get area, all it knows is that it's a shape. At this point, it doesn't even know if V is a circle or if it's a square. All it knows is that V is a shape. It's declared as a shape, right? It's not declared as a circle. It's not declared as a square. It's declared as a shape. It does know that the shape has a get area method because get area is defined as part of shape class. However, it's defined as an abstract method, but it is there. And so it goes ahead and allows that call to succeed. But at runtime, it has to figure out which version of get area to call. Is it going to call get area for a circle, or is it going to call get area for a square? And dynamic binding handles that. Polymorphism is when different objects refer differently to the exact same method call. And dynamic binding is what the Java virtual machine does in order to match the call with the particular method being invoked. So just before the Java virtual machine executes a method call, it looks at the method call's calling object. So it looks at my, my V shape, right? It looks at that particular object. And then it looks at the type of the object that's been assigned. If the assigned object is from that class, the JVM binds class X's method to that method call. If the assigned object is from class Y, the JVM binds class Y's method to the method call. So what it does is it just goes down as a little inheritance hierarchy to find the lowest version of the method that is available to us. And that lowest is a really dumb way of saying that. But let's see if I can. If I have a shape, right? And the shape has an abstract method called get area. And then I have a circle class, which has a non-abstract version of get area. And then I have a weird kind of circle called an oval that's inherited from it, right? Which also has a get area method. And then we have a square, right? And the square has get area. And then we have a special type of square called a rectangle. It ought to be vice versa, right? Which has get area. And then it comes down to the time when we have our function, you know, that takes a shape and then calls get area on it. What does it do? Well, it starts and it looks down the inheritance chain. It goes, okay, V is a shape. It comes up here and it looks, and then it tries to find the most specific version of the get area that will match. And so it just does a check. All righty. Is this shape a circle? Yeah, it is. So we could call that one's get area. So it binds this call at runtime so that it can invoke that get area. Now, is it an oval? No, that's too specific. So it doesn't bother going down to the bottom of that one. And then say that we called it again with a rectangle shape. It would jump down and start walking down the hierarchy list. It would go, okay, do we have a get area method at all? Yeah, we sure do. Well, let's find out which one it is. Are we a circle? Nope. So that means we're definitely not an oval. Are we a square? Yes, we are, but we're actually a rectangle. So yes, that one would work. But then it keeps walking down the hierarchy tree and it goes, okay, oh, but we have an even more specific version of get area that we can call. And so it would bind this call during runtime for that particular shape to call the one for rectangle. And then after the Java virtual machine binds the appropriate method to the method call, the JVM executes that method. Compilation details. If dog implements a display method that prints I'm a dog, would the following code work? Object obj equals new dog, obj.display. Is this good code? If we wrote a class called dog and it had a display method, could we do this? And the answer is no. Why? Because the object class has no idea that there is even a hint of a possibility of a display method. The object class does not contain a display method. You would have to cast it to be a dog in order for it to know. Well, then how come toString and dot equals and stuff like that work? That's because those methods are already in the object class, and so the dog class can override equals and toString. And so you can call, you know, dot toString on every dog, even, you know. Is that making sense? If the object at the root of the class, of the tree, my code, right? If he's got a reference to it, you can do things like this, right? I could do shape S equals new oval, right? Or I could do shape R equals new rectangle, right? Or shape C equals new circle, things like that. And then any methods that are listed as being part shape of part of the shape class can be accessed, right? So right now, our method, our shape class only has one or two different methods. Shape has a toString method and it has a get area method. So on any of these things, we can call get area and we can call get shape. It's legal to do that. If I go in here and I call, you know, r.get area, and then I call s.get area, and then I call c.get area, that's totally fine because every shape has an area and it's okay to do that. But what if I added a method to the circle class? Some really cool one like get circumference, public double get circum, which returns 2 pi r. Am I going to be able to come down here and call c dot get circumference, right? Int x is equal to c dot get circumference. And the answer is no, I'm not going to be able to do that, because all that the code knows at this point in time is that C is a shape. And do shapes have access to a get circumference method? No, they do not, right? A shape, all it has is get area and toString. Now we could check to see if it was a circle. If we wanted to do that, I mean, I guess we could actually put it in code up here. We could check to see which of these are circles, you know, but for shape V in the S list, if it is a circle, if V instance of circle, then it's safe to call the circumference, right? So I'm going to copy that and paste that and change it to our call. That has a circumference of, and then call get area. Get circum. What did I call it? Circumf. But notice that it's not even letting me hook it up like that. Where's my circle class? Okay, I called it get circum. It's calling that an error. Why? Because all it knows about V is that it's a shape. We would need to cast it. We could do that. We could say, I need the circle version of V so that I could then call get circumference on it. Now that looks a little cryptic. That may look a little bit too cryptic. So if I was trying to write it in a way that would be easier to understand, I would separate the casting and the calling of it. And so I would say circle, you know, CV equals circle V. I would cast that object into a circle reference. And then when I wanted to print it out, I could call out that thing. I was not able to call c.get circumference because a shape does not have a get circumference call, not even an abstract one. But I was able to test it to see, oh, by the way, are you a circle? Are you an instance of the circle class? If so, let's go ahead and cast you into a circle reference so that we can call that. Now, dynamic binding does that work for us if that root class, that superclass, the shape class, has an abstract method called get circumference, but not everything has a circumference, right? So we couldn't stick that in there, right? What would happen if we said we want to get the circumference of a square? Well, maybe we could decide that we're going to call them get perimeter instead of get circumference, since that would apply to all shapes. But in particular, we have some things that apply to one specific kind of thing and some things that apply to all types of that hierarchy. And so you put the things that are specific to each class in the subclasses, like square and circle, and you put the things that are common to all of them inside the base class, the root class, the superclass. All righty. I wish that we were face-to-face so I could look to see how boggled people were or how bored they were or what. Is that making sense? Somebody pretend they
Yep.
are. Yeah, I see you all nodding. Yep. Okay, so we're going to need to quit soon. Polymorphism with arrays. We've just demonstrated that, except we used array lists. You can step through the array, and for each array element, you call a polymorphic method. For that to work, you have to make the array the type of the superclass, not the subclass. Because I want to store both circles and squares in my array, it could not be declared as an array of circles or as an array of squares. It had to be an array of shapes, right? So shape S array equals new shape, 2 of them. And so S array, the first one is a new circle, radius 10. The next element in the array is a square of side length 11. And then I could step through that and call get area on each one of them if I wanted to, right? So double total area equals 0 for every shape in the S array. Add that to the total, right? Total area plus equals v dot get area, right? Like that. And even though they are different types of objects and the calculations to determine their area are completely different, polymorphism and dynamic binding lets this happen. All righty. I think the piggy bank program is probably interesting enough that I don't need to pile another homework assignment on y'all, especially since I want you to be working on your projects as well. So why don't we call the lecture done? Where did we stop? We stopped on page 22, and I'll make a Dropbox for us. And so Troy, I will look at assigning the pictures into the graphical user interface, and I'll send you some demo code to do that, or I'll record a little lecture, or maybe we could set up an appointment to Zoom together to get that to work.
All right.
It's absolutely doable.
Excessively complicated.
It shouldn't be excessively complicated once we get it. Once we do it, it's going to look okay. I'll correct the typos in a bit. All right, it's there to upload into. All right, so I will see y'all next week. Please contact me if you have any more questions, and Troy definitely will be getting with you over that on the weekend.
Thank you. See you next time.
All right.
Thank you.
Thank you.